and I will share my screen. Okay, can you see my screen? Can you hear my voice?
Yes, Doctor.
Okay, thank you for the response. Okay, last week we have gone through this the last part of chapter 5, which is about the wave propagation. Okay, and I think we have gone through up to wave absorption. Okay, we have gone through up to wave absorption, and today we're gonna finish all the chapter 5. Okay, regarding the wave propagation. Okay, so maybe before we start again, before we continue, maybe we can refresh what we have learned until now. Okay, again I would like to draw my favorite picture. Okay, channel, we have a transmitter, we have the medium, the channel, we have the receiver part over here. Okay, so now in this topic, what we're gonna learn is about the characteristics of the electromagnetic waves that travels from the transmitter to the receiver side. Okay, so we're gonna learn about this wave. Wait, So what we're going to learn is about the characteristic of the waves, of the transmitted wave that travels into the medium from the transmitter to the receiver. Okay, so from here we can see that in this slide, okay, so this is the third part of chapter 5. Okay, if you remember the second part of chapter 5, we are learning about the antennas. And in the first part of chapter 5, we are learning about the transmission line. Okay, mainly about the cables and also the type of mediums. Okay, so the cables is this one, and also can be the cables that connected transmitter to the receiver. Now in the third part, which is the last part of chapter 5, we're going to learn about the characteristic of the electromagnetic waves. Okay, so electromagnetic waves can be divided into a few categories, what they call as a radio wave, infrared, ultraviolet, X-rays, and gamma rays. So radio waves are the waves that are the common terms that normally used to describe the frequencies band for the communication systems. Okay, we call it radio wave. So it is a common term for the wave that use the frequencies in the communications. Okay, in the wireless communications. And then infrared, normally in the optical systems, which is higher frequencies in the gigahertz. Ultraviolet, higher frequency. X-rays, much more higher. Gamma rays, much higher frequencies. Okay, so the moving to the right side, the frequency is going to be much higher. Okay, and we have seen about the wave attenuation, which is defined as the ratio of two different power density. Okay, so the ratio of two different power density within at certain range of distance compared to power density at another distance. Okay, So for example, here we have the antenna over here, and here is the distance R1, okay, and we have another one here, which is the distance R2. Okay, R2 is further away compared to R1. So the ratio of power density P2, P density of distance 2, divide with the power density at distance 1. So this is what we call as the wave attenuations. Okay, so if you see from these equations, power density 2 over power density 1, so power density is equal to power divided with 4 pi r square. So this is supposed to be this is using the example of isotropic radiator where the gain is equal to 1. So actually there's another one here multiplied with GD. Okay, so power radiation multiplied with directivity gain for distance 2 square, 4 pi r2 square, divide with another power density at the shorter distance, P radiations multiplied with GD, divide with 4 pi r1 square. Okay, so the ratio you're going to get R1 over R2. So this is a parameter without a unit. It's a unitless parameter. And it is also called as a space attenuation. Okay, and we can express this wave attenuation parameter in terms of decibel. Okay, so the parameter is alpha equal to 10 log of power density 2 over power density 1, which is equal to 10 log of R1 over R2 square. So you see that R1 here, okay, when we do the division, it's going to be at the upper side. Okay, so it's going to be R1 over R2 square. And then wave absorption. Okay, so again, if I draw this, okay, so as the wave travels from the transmitter to the receiver, okay, so the wave will collide with many things, okay, including the molecule, water molecules, the atoms, and rain particles, water particles, gas, and even obstacles like buildings, trees, and so on. Okay, so when the wave collide with obstacles, okay, some or all of the energies of the wave will be absorbed by that thing, the thing that collide with the waves. Okay, the obstacles. Okay, for example, here, example of wave attenuation, wave absorption here is a water molecule within the atmosphere, where it will absorb some of the energy of the waves. So what happens is that when some of the energy is absorbed by that obstacle, okay, by the water molecule in the atmosphere, the wave gonna be attenuates. Okay, attenuates here means in Malay we call it as a pelemahan signal. Okay, so attenuates that we have learned previously is one is due to the distance, number one. Another one is due to the absorption. Okay, absorption by many things. Some of the elements in the medium, for example, like water molecules, the air particles, gases, rain, even for the trees, buildings, and so on. Okay, so what happens is that some or all of the energies of the waves will be absorbed. The wave gonna be attenuates. Okay, as it moves, as it travels through the medium. Okay, and we have seen about wave absorption, especially for the rain attenuations, where this is more significant for the waves that has frequency 10 gigahertz and above. Okay, so wave that has frequency 10 gigahertz and above are more prone to the wave absorption, mainly due to the water molecule or the rain. Okay, I gave example previously in class about the situation, the condition for astro satellite television. Okay, if you remember last week, I said that Astro is a satellite television service which operate at gigahertz frequencies. So the frequency is larger than 10 gigahertz. So what happened is that especially during the heavy rain, okay, you will experience that there is no signal. Okay, so people blame the Astro because of these issues. Whenever there's a heavy rain, there's no signal. Okay, so the issue is it's not due to the Astro actually. It is actually based on these situations where during the heavy rain, okay, so the signals that travels from the satellite to your home, okay, so as the signal travels, the rain will absorb the energy of the signals and the signals will attenuate. So due to the long distance, it will keep on attenuates until the amplitude level drops below the threshold limit. Then the receiver unable to capture the signal. Okay, so frequency more than 10 gigahertz. So this is related to the wavelength. Okay, if you remember wavelength C over F. So the higher the frequency, the smaller would be the lambda. Okay, so at 10 gigahertz and above, the size of a wavelength will be smaller than the size of raindrops. Okay, so that's why during the heavy rain, signals that has a lambda less than the size of the raindrops will have a significant effect. Okay, so that's why if you see now, Astro is moving towards fiber optics. Okay, they are moving their services to the fiber optics together with the internet. Okay, so that's about the wave absorptions, and this is a graph about the water vapor and also the oxygen molecule that absorbs the signals. Okay, absorb the energy of the signals, which will cause the attenuations. Okay. Okay. The next topic is about wave refraction. Okay. So what happened if the wave moving from one medium to another medium? Okay, so wave refraction is the phenomena that happens when the wave travels at two different medium that has different density. Okay, so when the wave travels from a medium that has less density towards more dense density, higher density, the wave is not travel at a straight line. Instead, it will bend to a different direction. Okay, so this is what we call in Malay as the pembiasan. Okay, if you see here, this is it shows how refraction happens. So when the wave travels from medium 1, which is less dense, okay, so it travels in these directions. In these directions, you're gonna see that instead of going straight, okay, the wave will bend into a different angle. Okay, the wave will bend into a different angle. Okay, and this is where we have learned, I think you have learned this in the secondary school, about the Snell's law. Okay, remember Snell's? Okay, I think you learned this in physics subject during your secondary school, how to calculate the angle of refraction, which is what we call in Malay as a pembiasan. Okay, so this is refractions. Okay, refractions when the wave travel at two different mediums that has different different values for the densities. Okay, and then a reflection. Reflection occurs when an incident wave strikes a boundary of two media. Some or all of the incident power does not enter the second material. Instead, it will be reflected. Okay, so this is example of reflection where you see that the wave travel in these directions. Okay, instead of going through the medium 2, it will be reflected back to the same medium. Okay, so this is what we call as the reflection. In Malay, we call it as pantulan. Okay, diffraction. So diffraction is defined as the redistribution of energy within a wavefront when it passes near the edge of an opaque object. Okay, so it is a phenomenon that allows the radio wave to propagate around the corners. Okay, so this is example of diffractions. Okay, in Malay we call it as a Cerakan Glombang. So when the wave travel through the gap, you see that the wave travel through the gap. You see what happened. So this is the gap. Okay, so it will spread out like this. Okay, and similar with this one, when the wave hit the edge of the object, okay, it will goes around the obstacles. Okay, you see that the wave travel in these directions and it will goes around the obstacles like this. Okay, so this is what we call as the diffraction. Okay, so in the previous final exam we have asked these kind of questions. We asked the student to explain about reflection, refraction, and also diffraction. Okay, we have asked this kind of question previously. So what we asked in the question is that we asked the students to give brief explanations about their understanding about the refraction, reflection, and also diffraction. Okay, so this kind is we have asked this a few times. Pernah ditanya beberapa kali. Okay. Interference is the another signal that has the same frequency as our signal. So that signal will be called as the interference. Okay, so the collided of two different signal that has the same frequency, this is what we call as the interference. Okay, ada signal yang mempunyai frekuensi yang sama. So signal itu bila bertembung dinamakan sebagai interference. Okay, so that signal, another signal, is the interference to your signal. Okay, so this is about the interference. Okay, from two different waves that has the same frequency. Okay. Okay, so now let's look into the free space laws and phase transmission equation, and this will come out in the final exam. Okay, again you see my favorite picture. Okay, the transmitter, the receiver, and also the medium. Okay, so again we refresh what we have learned previously. So This is the second, this slide has been shown twice in chapter 5. So previously you have seen this slide in the previous topics. So now let's refresh again about the important parameters. Okay, so this is a transmitter. So the transmitter produces power, which is what we call as a PT. Okay, power transmit. And this signal goes through the transmission line towards the antenna. Okay, and within this transmission line there's going to be losses, which is defined as the LT parameter. Okay, and if you see that the power supplied to the antenna, this is what we call as the P input to the antenna. And if you see that after the signal is supplied to the antenna, some of the energy will be dissipated. Okay, some of the energy will be dissipated as dissipation as a heat. Okay, and most of the power will be used for radiations. Okay, which is what we call as a P radiation. And this antenna has a gain what we call as GT. Okay, and the signal is transmitted into the medium. Okay, and theoretically we learned that the signal will move in a spherical shape. Okay, until it reach the receiver. So the distance here is R in meter. Okay, and at distance R we can calculate the power density. So power density is equal to EIRP. Okay, EIRP divided with 4 pi d square. EIRP divided with 4 pi r square. Okay, the surface area of a spherical. Okay, and EIRP, again EIRP is the power radiation multiplied with directivity gain, or you can say that it is P input multiplied with GP. Okay, and this receiver antenna has a gain GR, and the power output from the receiving antenna is what we call as a P out. And the signal goes through the transmission line, and it will have a losses over here, which is defined as LR, the losses. Okay, and the power received by the receiver, this is what we call as the PR. Okay, power received by the receiver. Okay. Okay, so in order to use what we call as a Friis transmission equation, okay, we need to use a Friis transmission equation in order to find the received power. Okay, we actually want to find the received power. So in order to calculate the received power, we can use the Friis transmission equation. Okay, so if you see from here, EIRP in this case is defined as the P input multiplied with the antenna gain. Okay, which is P in multiplied with GT. Okay, at distance D or distance R from the transmitter, we can calculate the power density, which is equal to P in multiplied with GT divided with 4 pi d square or 4 pi r square, where this is the EIRP. Okay, and then what? So from this equation we can calculate the P out. Okay, so P out is the power output from the receiving antenna. Okay, which is this one, P out, the output power from the receiving antenna. Okay, is equal to PD multiplied with effective area of the receiving antenna. Okay, AE is the effective area of the receiving antenna. So remember, PD is watt per meter square, and this one is effective area. The unit is meter square. So watt per meter square multiplied with meter square. So you're gonna get a value in terms of watt. Okay. So this PD, power density, is P in multiplied with GT. So we can put inside the equations. Okay, P input multiplied with GT divided with 4 pi d square multiplied with AE. So now the issue is how much is AE? Okay, how much is AE? So AE, okay, the effective area of the antenna is equal to the antenna efficiency multiplied with the actual antenna dimension. Okay, actual area of the antenna dimension. Okay, the actual size. So effective area, you know that in your syllabus, the area of the antenna is assumed to be a circular shape. So in your syllabus, we are actually using the parabolic antenna, where we assume that the surface of the antenna is in a circular form. Okay, circular form. So here, this A is actually pi r square of the antenna. Okay, the effective surface, the actual surface area of the antenna, which is in a circular shape. So it is a pi r square multiplied with the antenna efficiency. So you're gonna get effective area of the antenna. Okay, so from here, from here we can actually we can also define the parameter of GR. GR, the gain of the receiving antenna, is equal to 4 pi AE. Okay, 4 pi AE divided with lambda square. Okay, so 4 pi AE divided with lambda square. So this equation can also be used for GT, to find the GT parameter. So GT, okay, normally in the question we give you the same antenna. Transmitter antenna and receiving antenna are same antenna. Okay, normally like that. Okay, normally like that. Okay, if different, then no problem. We can find later about the GT. Okay, so GR is equal to 4 pi multiplied with effective area of the antenna divided with lambda square. So from here you can see the relationship of AE. So we can rearrange the equations to become like this. AE equal to GR lambda square over 4 pi. Okay, so we're gonna get this in terms of meter square. Okay, so this is parameter in terms of meter square. Okay, so put inside the equation. Okay, put inside the equations. So P out, the output power from the receiving antenna, is equal to the power density multiplied with the effective area of the receiving antenna. So you're gonna get P in multiplied with GT divided with 4 pi d square multiplied with GR lambda square over 4 pi. So therefore, P out, after we rearrange the equations, we're gonna get P in multiplied with GT multiplied with GR multiplied with lambda over 4 pi d square. Okay, so here the unit is in terms of watt. Okay, and then what? So from these equations, okay, from these equations, this is what we call as the parameters inside the bracket. This is what we call as the free space loss. Okay, the free space loss. Okay, so the free space loss is known as the free space propagation loss. it is sometimes this one, it is sometimes more convenient to inverse so that it is in decibel value would be positive value. Okay, so the way we're gonna write the free space loss, so if you see from here, so this is actually the free space loss. This is kind of losses due to the distance. Okay, so the free space loss, normally when we write the free space loss, it is, we inverse it so that when we change into decibel, it's gonna produce a positive value. Okay, so this is just for the notation of in term of decibel. So we can write like this: FSL in term of 20 log 4 pi d over lambda. So you see that we inverse it, we inverse the equations. Okay, so that we're gonna get a positive value of FSL. Okay, and if you see, we can rearrange the final equations to be like this: P out, okay, P out is equal to P in multiplied GT multiplied with GR. So this is if only we consider the free space loss in the medium. Okay, so if there's more losses, for example LT and LR, this one, what about this one, LT and LR? Where should we put this one? Okay, LT and LR. LT is the losses in the transmission line. LR is the losses in the receiver transmission line. Okay, so if there's another losses over here, we can put the losses in here, LT multiplied with LR. Okay, so this is, we divide the values in terms of absolute values. Okay, so we divide with the free space loss, divide with the LT, divide with the LR. Okay, if we have another losses. Okay, so therefore, if we want to represent the power in terms of decibel, okay, in terms of dBW, this one, so dB in terms of decibel, the process of multiplication in absolute value is represented as addition process in decibel, whereas the division process in absolute value is represented as subtract process in the decibel. Okay, so dalam untuk proses darab dalam absolute value, apabila kita melakukan proses dalam decibel, maka kita perlu buat dalam sebutan tambah. Manakala untuk bahagi, proses bahagi dalam absolute value, ianya adalah proses tolak dalam decibel. So be careful about this. So this is what I saw many careless mistakes about this issue. About in decibel, we cannot do multiplication, we cannot do division in decibel. Okay, when we want to write in decibel, either it is plus or minus. Okay, so you see from these equations, we multiplied P in, GT and GR. Therefore, in decibel, we're going to need to add all of this. Okay, so this is, for example, here in dBW. Okay, so P in dBW, GT in dB, GR in dB, okay, minus, so you see that everything after here, okay, minus, okay, everything after here gonna be the losses. Okay, so here is a FSL. Okay, so minus all the losses. If we have LT, LR, so we can do minus another one here. If we have LT, LR, so you see that here. So if you have LT and LR like this, so we need to do minus LT in decibel, okay, and another one minus LR also in decibel. Okay, so everything here is losses. Okay, So again, okay, you see that here is PR. Okay, so don't confuse about P out and PR. Okay, so power received, okay, the power received by the receiver, if we consider the losses in the transmission line LT and LR, then we can write like this. Okay, PT multiplied with GT multiplied with GR, divide with divide with the free space loss, and also the LT and LR. Okay, so these are the power received by the receiver. Okay, so if let's say there's no other losses other than the FSL, okay, this one is enough up to here. That means P out is equal to P received. Okay, so if you see the picture, here, okay, if we assume, so if we assume there is no LT, no LR, that means the output power is the same as the received power to the receiver, because there's no other losses other than the free space loss. Okay, so that's why in the slides, in the lecture notes, you see that when we want to consider everything, okay, every losses, so we can use the terms PR, okay, because PR involve the transmit power, the EIRP, and also the free space minus the free space loss minus the LT and also the LR, okay, the losses. So that's why, okay, when you want to consider everything, okay, so that means PR, the power received, is equal to PT GT GR divide with FSL divide with LT and LR. Okay, so if you want to express in terms of decibel, okay, for the received power, so received power is equal to, so assuming that this is dBW, this is also dBW, this is dB minus all the losses. Okay, this is all the losses. So this is FSL, okay, LT and also the LR. Okay. Okay. So if let's say there's no LT or LR, okay, sekiranya tidak ada LT ataupun LR, you can use up to here. That means P out is also a received power, as I mentioned earlier. If there's no LT or LR, P out is equal to the received power because there's only the free space loss. Okay. In the next example, you're gonna see that the next example shows that there's only FSL loss and there is no LT, there is no LR in the next example. Okay, so let's do the example, the last example in your notes. Okay, example 14. So a microwave link is to be set up between two cities which are 100 kilometers away. Okay, so when you receive this kind of question, I suggest you to draw. Okay, so you see that here, this is a transmitter. Okay, the transmitter. Okay, so the distance is 100 kilometer, which is 100,000 meter. Okay, so the link will be operate at 3 gigahertz. Okay, so frequency is f equal to 3 gigahertz. So from frequency, actually you can calculate the lambda. Okay, lambda is equal to C over F. Okay, so C is 3 times 10 power of 8 divided with 3 times 10 power of 9 giga. Okay, so you're gonna get here 0.1. Okay, so and then these two microwave link using a two parabolic horn feed antenna at both transmitter and receiver. So both transmitter and receiver use the same type of antenna. We can assume that in this case, in this example, both antennas are the same, as the same parameters. Okay, so the parabola are 1 meter in diameter. That means R diameter radius is 0.5 meter. Okay, and are 80%. So efficiency is equal to 80%. Efficient in radiating the input signal. If the input signal is 21, okay, that means P input is equal to 20 watt. Find the gain of the antennas. So from this example, you can see that both antennas are the same. If both antennas are the same, that means all parameters of the antenna is the same. That means GT gonna be equal to GR, because we are using the same antenna. Okay, so to find the gain, we can calculate based on the GR parameters, which is as stated in this lecture notes, 4 pi AE over lambda square. Okay, so we can find GR is equal to 4 pi AE divided with lambda square. So we already find the lambda, 0.1 meter. AE is the effective area of the antenna. So efficiency multiplied with the actual area. So efficiency is 80% or 0.8 multiplied with the actual area of the antenna surface. So this is a parabolic antenna, and the surface of the parabolic antenna is a circular shape. So that's why the area is pi r square. Okay, and then what? If you see from here, 0.8 multiplied with a circular area of the antenna, which is pi multiplied with the antenna radius, 0.5. So 0.5 from 1 meter of diameter, we divide with 2. Diameter of antenna is 1 meter, so therefore the radius is 0.5. Okay, so we get the effective area 0.628 meters square. So put inside the equations, so you can find the GR. GR equal to 4 pi AE over lambda square. So 4 pi multiplied with 0.628 divide with 0.1 square. So we get 789.168. And this is also same as GT, because GT and GR are the same in this example. Okay, and then what? So the question asks to find EIRP. So EIRP is equal to P in multiplied with GT. Okay, so P in multiplied with GT. So this is, since GR is similar with GT, okay, in this example, since GR is equal to GT, so that's why it puts a GR over here. So it is a P in multiplied with the gain. So you're going to get 20 multiplied with 789.168. So this is what we have obtained previously from the GR parameters. So GR and GT are the same. So we get 15783.361 watt. for the EIRP. And then what? Then the question asks, find the power density PD at the receiver. So that means find the power density at 100,000 meter away from the transmitter. Okay, so power density is equal to EIRP, which is P in multiplied with GT divided with 4 pi d squared. So remember, this is supposed to be 100,000. Okay, this is supposed to be in terms of meter. Okay, so let's try whether the answer is correct or not. So 15783.361 divided with 4 pi multiplied with 100,000. Okay, so the answer is correct. So this is supposed to be 100,000, 100,000. Okay, in terms of meter. So you get the power density is equal to 1.256 times 10 power of minus 7 watt per meter square. Okay, and then what? Then the question asks, find the free space loss, FSL. So normally when we mention about FSL, normally we need to find the values in terms of decibel. Okay, in practical case, normally when we mention FSL, normally we want to know how much is the value in terms of decibel. Okay, so that's why here FSL is equal to 20 log 4 pi d over lambda. D is the distance from transmitter to the receiver. So 20 log 4 pi multiplied with distance 100,000 meter divide with lambda 0.1. So we're going to get free space loss 141.984 decibel. Okay, and then what? The last question asks to find the output power from the receive antenna. So the question asks about P out. Okay, so if you see from here, from these questions, okay, yeah, okay, P out. So if you see from this question, there is no LT, there is no LR. Okay, dalam soalan ini tidak ada losses LT, tidak ada LR. Sorry, this is okay. There is no LT, there is no LR. That means there is no losses in the transmission line. Okay, there is no losses in the transmission line. So this is for this example. That means the losses is due to the free space loss only. Okay, so that means if there's no other losses, that means the P out is actually the receive power. Okay, so P out is also PR, the receive power, because there is no other losses. So that's why you're going to see later that the solution in your notes keep on changing between P out and PR. Okay, dalam nota ini dia bertukar-tukar antara P out dan PR kerana tidak ada losses yang lain selain daripada FSL. So don't be confused. Okay, so if you see from here, so it starts with PR. So remember, PR here in this example is same as P out. Okay, because there is no other losses other than the FSL. Okay, so PR or power receive or power from the receiver antenna is equal to P total. So this is in terms of dBW, dBW. P transmit in terms of dBW. So you see that it uses P transmit. Okay, So why not use P in? So P transmit is equal to the P in, because there is no LT, there is no losses in the transmission line. Okay. Again, if I show you the picture, so you see that here PT, okay, and here is P in. Okay, so if there's no LT, that means PT is equal to P in. Okay, so all the power produced by the transmitter will be received by the antenna. Similarly, on the receiver side, all power produced by the receiving antenna will be received by the receiver. Okay, so don't be confused with these solutions. Okay, so from here you see that PT in dBW plus gain in dB plus transmitter gain, transmitter antenna gain plus receiver antenna gain in dB minus losses, which is FSL in terms of dB. Okay, so we have calculated previously about how much is the P in. P in, which is similar, which is equal to 10 log 20. So it is given in the question that the input power is 20 watt. So 20 watt in terms of dBW, 10 log 20, so you get 13 dBW. So this is equal to the PT, power from the transmitter, because there's no losses LT. Again, the receiver antenna gain, we have calculated this one, 789.168, which is same as the GR. Okay, GR and GT is the same. Okay, which is 28.97 dB. And we have calculated the FSL previously, which is 141.984 dB. So now we can put inside the equations. Power received is equal to 13, okay, dBW. Okay, so this is a dBW plus GT 28.97 plus GR 28.97 minus 141.984 dB. So be careful here. Every parameters here in terms of decibel. Okay, so I hope that you are not doing careless mistake again in the final exam. I saw many students in the test do this careless mistake, so be careful. Okay, so this is minus 71.044 dBW. Okay, this is the received power by the receiver, which is also similar, same as the P out, because there's no other losses other than the FSL. Okay, and then what? There's another question. Okay, state your assumptions, if any. Okay, so what is the assumption? The assumptions here is that there's no other losses other than the free space loss. Okay, tidak ada losses yang lain selain daripada FSL. So that's the assumption, because the transmission line loss is not given in the question. So we assume that the losses only due to the FSL. Okay. So do you want to ask question about this? Any question?
No.
Can I get your response? Are you still there?
Yes.
Okay. Anybody want to ask question? Ada soalan nak tanya? So this is one of the favorite question that will come out in the final exam. If you see in the question bank, we can say that almost every semester this kind of question will come up. Okay, almost every semester this kind of question will come out for question number 5, and it will come out again in this semester. Okay, akan keluar lagi pada semester ini, something like this. Okay, anybody wants to ask question before I want to show you the last example? Okay, so no, seems like no question. Again, can I get your response? Are you still there?
Yes, Doctor.
Okay, saya risau saya terputus. So I hope that you understand this. Okay, I hope you understand. And maybe you don't have question now. Maybe you want to ask later. No problem. Boleh tanya kemudian. Okay, you can ask later if you want. So that's why we need another example so that you can have a better understanding about this kind of questions. Okay, so if there's no other questions for this, tak ada soalan. So I want to show you another example. Let's do one question from the previous semester final exam. Okay, maybe it is good for you to see these previous questions. Okay, so I'm gonna stop this for. I'm gonna change to another. So this one. Okay. So this is fun. Okay, again, can you see my screen? Can you see my screen? Can you hear my voice? Boleh, Okay. So this is the previous semester final exam, semester 1. Not last semester. This is 2020-2021. So we are now semester 2, 2021-2022. So this is what we can say that 1 year, one and a half year previously. Okay, so again, this is not this semester. So I hope that I'm not opening the this semester question. They're gonna be big problem. Okay, kalau saya terbuka soalan semester ini akan jadi big problem. Okay, so at that time is online exam. So that's why open book. Okay, there's an open book. So what I want, you see that question 1, 2, 3. Question 3. So we have 5 questions. Okay, we have 5 questions. Each questions for each chapter. Okay, 1 question for each chapter. Okay, so let's look question number 5. Okay, question number 5. So the characteristic impedance of a transmission line must be equal to the load impedance for maximum power transfer. Discuss the concept of characteristic impedance with the help of a diagram by looking into perspective of a finite length of transmission. So this is in the notes about the definition of the characteristic impedance. Okay. So based on your understanding of a mismatched load, sketch the formation of standing wave from the incident and reflected wave. So you need to sketch a standing wave which consists of incident wave from the source to the load, and also the reflection wave from the load to the source, which combined together it's gonna be as a standing wave. Okay. Again, this is the picture in the notes. You can see the picture of incident wave, reflected wave, and there's a standing wave. So you need to sketch three of it: incident wave from source to the load, reflected wave from load to the source, and the third wave gonna be the standing wave. Okay. And question B. So this is the question that we want to. To find the solution. Okay, to find the solution. A telco company in Malaysia has decided to set up 2 base stations to improve the coverage area. Okay, so the distance between 2 stations to be 200 kilometer. Okay, 200 kilometer. That means 200,000 meter. Okay, with the line of sight communication link. So in order to communicate with each other, the requires below must be fulfilled. Okay, so it use an antenna with a power gain of 10 dB for each station. Okay, so the antenna gain is 10 dB for both. So that means a transmitter and receiver are using the same antenna. Okay, frequency of operation of a communication link is 1.8 gigahertz. So this is the frequency. The transmitter produces 9 watt of power, which is fed to the transmit antenna via a 45 meter transmission line with characteristic impedance of 50 ohm. Okay, so that means the transmitter produce 9 watt of power. So this is actually PT, power from the transmitter. So power from the transmitter was fed into the transmission line, okay, and arrive at the receiver. So the transmission line has a length of 45 meter with the Z naught equal to 50 ohm. So the last one, the transmission line attenuates 8 gigahertz. Okay, attenuates 8 gigahertz. Attenuates at 1.8 gigahertz per 100 meter. Okay, so attenuates 8 dB. Okay, sorry, the transmission line attenuates 8 decibel. Attenuates 8 decibel radio frequency signal at 1.8 gigahertz per 100 meter. So that means so this is supposed to be 1. So this is LTH 6. 45 meter per 100 meters. So per 100, okay, so that means 1.8 dB. So this is supposed to be not gigahertz, and this is supposed to be 1.8 dB per 100 meter. Okay, 1.8 dB per 100 meter. So this is supposed to be 100 meters. So the distance is 45 meter, and I get a 50.6. Wait. 1.8 gigahertz, 1.8 gigahertz per 100 meter. So this is 8 dB. So 10 is 8 dB at 100. Okay. So 45. Okay, so you see that the transmission line attenuates 8 decibel, okay, at frequency 1.8 gigahertz for each of the 100 meter. For each of the 100 meter of cable, okay, from the transmitter to the antenna, it will attenuate 8 dB. okay, for every 100 meter. So since the transmission line is only 45 meter, you see that the transmission line is only 45 meter. So the attenuations LT gonna be less than 8 dB. So 8 dB is for every 100 meter. So if we get the ratio 45 meter divide with 100 meter multiplied with 8 dB, okay, so you're gonna get around 3.6 dB. Okay, so this is for the LT. Okay, so if you see that from here, so this question, okay, this question is only the losses over here, okay, the losses over here is only due to this. So that means there is no LR. LR is not mentioned over here, okay, because here it is only mentioned that the transmitter produced 9 watt of power and it is fed into 45 meter of transmission line. And regarding this transmission line, it is said that the transmission line actually attenuates at 8 dB for every 100 meter. Okay, so 1.8 over here is the frequency that we use actually. Okay, if you use other frequencies, that means the attenuation gonna be different. Okay, so that means in this question, it is not specified how much is LR. Okay, so LR in this example, in these questions, is actually 0. We can assume that there is no losses in the receiver transmission line. Okay, because this is only for the transmitter side. Okay, the question is only mentioned about the transmission line, transmitter side. Okay, soalan ini hanya menerangkan tentang keadaan yang berlaku pada transmitter. Okay, if the question specified that the receiver transmission line has a certain characteristic, then you need to calculate how much is LR as well. Okay, for now, for this question, it is only referring about the LT. Okay, so let's do this. Power at the output of the antenna, power at the input of the antenna, assuming that a matched load in watt. Assuming that a matched load in watt. So how to calculate this? So the power input to the antenna. Okay, so how to do this? That means if we draw this one. So this is LT, this is LT. So this is LT and this is a power input. Okay. And then what? And then okay. So if it is a matched transmission line, that means there's no return path. There's no reflected wave. So that means there is no other losses other than the attenuation by the transmitter, the attenuation in the transmission line. Okay, so that means in this case only LT is will attenuate the signal. Okay, so therefore in order to find this, first you need to find the PT In the question it is given as, you see that here 9 watt. Okay, the transmitter produced 9 watt. Okay, so 9 watt in terms of decibel it is going to be 10 log 9. 10 log 9. So you're going to get this equal to 9.542 9.542 dBW. Okay, so let's calculate together. Mari sama-sama kita kira. And then what? Attenuations. Okay, so attenuation in 45 meter, okay, line is equal to, so this is equal to, since this is only 45 meter, so that means 45 per 100 multiplied with 8 dB. Okay, so you're gonna get 3.6. Okay, so therefore the power input to the antenna, okay, the power input to the antenna, P in, is equal to P from the transmitter minus LT. So this is, all of this is in terms of dB, decibel. Be careful. So that means this is equal to 5.7.94. So 9.542 dBW minus 3.6 dB. So we're gonna get this equal to 5. Okay, so 9.5.2 minus 3.6, 5.942. Okay, so this is 5.942 dBW. Okay, which is equal to, so the question asks in terms of what? So you're going to need to do the anti-log. Okay, you need to do the anti-log, which is, you're going to get anti-log of 5, this one, so anti-log 0.5942, you're gonna get 3.928. Okay, so 3.928 watt. Okay, can you understand this? Ada soalan nak tanya? Any question? You are still there, right?
No. Yes.
Okay. So P input to the antenna, we consider power from the transmitter minus the losses in the transmission line. Then it will be arrived at the antenna. Okay. And then what? Effective EIRP that we have learned previously, EIRP is equal to P in multiplied with GT. Okay, so this is actually equal to P in, our P in is Okay, so the G is given as 10 dB. So this one. So this is GT and also GR. Same. Okay. So therefore you can do like this, P in dBW plus, because the question asks in dBW, plus GT in dB. Okay, so therefore you can use 5. This is from the previous question, 5.942 dBW plus 10. Okay, so this is equal to 15.942 dBW. Okay, so the free space loss. So how to calculate the free space loss? Okay, remember free space loss in dB. So that means FSL is equal to 20 log of what? This one, 20 log of 4 pi d over lambda. Okay, so 20 log of 4 pi d, the distance between transmitter to the receiver, okay, divide with lambda. Okay, so now we know the distance. The distance is given in the question, which is 200,000 meter. Okay, and we want to find, but the parameter that we don't know yet is lambda. How much is lambda actually? So lambda is equal to C over F, speed of light divided with the frequency. So this is 3 times 10 power of 8. Okay, speed of light is 3 times 10 power of 8 divided with 1.8 gigahertz times 10 power of 9. Okay, so you're gonna get this equal to 0.17 for lambda. Okay, so try to calculate as well, so that we can find the correct answer. Okay, sometimes I do careless mistake. I wrongly calculate the values. Okay, so sometimes the students inform me there's something wrong with the answer. Okay, so you need to check my answer as well. Okay, so this is 20 log, okay, 4 pi multiplied with 200,000 meter, divide with lambda 0.17. So you're gonna get this 143.4 dB. Okay, so try use your calculator and try calculate and whether you can get 143.4 dB or not. Okay, and then what? Okay, power density. Okay, so power density is equal to EIRP divide with 4 pi r square. Okay, so EIRP divide with the spherical area based on the distance from transmitter to the receiver. Okay, so it is equal to, so power density is equal to P in multiplied with GT, okay, divide with 4 pi r square. Okay, so this is equal to, so P input, we have calculate the P input from the, so P input, this one, so 3.928, so we have calculated this from the first question, which is 3.928 watt, multiplied with antenna gain. So gain in 10 dB, so anti-log of 10 dB, you're gonna get 10. Okay, so anti-log, so GT equal to GR equal to 10 dB equal to 10. Okay, so anti-log of 10 dB is equal to 10. Okay, divide with 4 pi multiplied with 200,000. Okay, so you're gonna get the answer, square, this is square, so you're gonna get the answer equal to 78.145 this is a picowatt per meter square. Okay, pico means times minus a power of minus 12. So try use a calculator. 3.928 multiplied with 10 divide with 4 pi multiplied with 200,000 square. So you're gonna get 78.145 picowatt, okay, because it is power of minus 12 picowatt per meter square. Okay, 78.145 picowatt per meter square. And the last question, power received at the receiving antenna, assume that there is no other losses. Okay, assume that there is no other losses. So the question has specified that there is no other losses other than stated in the question. Okay, so that means the losses only due to the FSL and due to the transmission line. Okay, so therefore what you can do is like this. So power received is equal to P from the transmitter, okay, plus GT plus GR. Okay, so all of this in term of decibel. Remember, all of this in term of decibel. Okay, minus all the losses, which is the FSL minus the LT. Okay, so therefore this is a PR in dBW. So therefore, so I afraid if I do like this, you will make a careless mistake. Maybe I will do over here. I will do over here. So let's cancel this one. So let's do over here PR. This is dBW equal to PT equal to PT in dBW plus GT in dB plus GR in dB minus FSL in dB. So I have to do this so that you are not making careless mistake. Minus LT in term of dB. Okay, so we already found all the answers. Okay, So PT in dB, so 9 watt, okay, 9 watt is 9.542, okay, from we have so this is 9.542 dBW plus GT is 10 dB given in the question, another 10 dB, okay, because both antenna are the same, minus the FSL we get 143.4, so 143.4 dB minus the losses due to the transmitter transmission line, which is equal to 3.6 dB. Okay, so if you see above, okay, if you see above, for 45 meter of transmission line, the losses is only 3.6 dB. Okay, so we have found the answer from the first questions, okay, from the first questions, which is this one, 3.6 dB. Okay, so therefore you're gonna get the answer equal to minus 117.4458 dBW. Okay, and the question asks in terms of watt, so you need to change this into watt. So anti-log of this, you're gonna get 1.796, okay, sorry, picowatt. Okay, try use a calculator. Okay, anti-log of minus 11.7458, so you're gonna get 1.796 times 10 power of minus 12, okay, watt, so which is a picowatt. Easy, right? The question is not difficult. Okay, the question is not difficult for question number 5. Easy to score. Okay, so I open to questions and answer. If you want to ask question, if you don't understand, you can ask me now, no problem. Ada soalan tak? Okay, no question. Okay. So if you don't have any question, okay, if you don't have any questions, that's okay. And I suggest you to practice answer the previous semester final exam questions. Okay, because I can say that many of the questions are repeating questions where we only change the values. Okay, so what's the strategy? I suggest you everybody can take part. Okay, that means if you answer question number, for example, question number 2 last semester, then you share in the group. Other friends answer different question and also share in the WhatsApp group. So together you can build your own answer banks. Okay, I only have the question banks, so you need to produce the answer bank. Okay, so the questions are many in the question bank. So I believe you are unable to do but on your own. Okay, you need to have a strategy so that you can try to practice as many questions as possible. Okay, in order to do that, you need to collaborate with your friends. You answer question number 1, your friend question number 2, another friend question number 3, and so on. So together you can get as many answers as possible. And you can also ask me whether your answer is correct or not. Okay, so I suggest you, when you want to ask me questions about the previous semester final exam, I suggest you to do first. Try to answer the question first, then you can ask me about your answer whether correct or not. Okay, try to answer first. Don't worry whether it is correct or not. Just try to answer, and then the thing that you don't know how to do it, you can ask me question. Okay, rather than I start from the beginning, you should start from the beginning, and I help you to finish the answer. Okay. So I think that's all. Okay, that's all for today. And good luck for your final exam. Okay, good luck for your final exam. So maybe later, me and Mr. Ezri will share the hints. Or the specific topics that will come out in the final exam. Okay, so you need also to learn from the YouTube link that has been given in the WhatsApp group. Okay, for example, like the chapter 4, we have give you the link for chapter 4. Regarding what topic, I don't remember. That one is an important topic that will come out in the final exam. So try to learn from there. Also, other than my lecture video, we also have give you, previously we gave you a link in the WhatsApp group. Try to find the link about chapter 4. That one is important for your final exam as well. Okay. So that's all for today. So happy holiday. Okay, happy holiday to all of you. Oh, sorry, we need to take the attendance. Baik saya ingat je. Okay, can we take a picture or what? Do you want to take a picture together or no need? Maybe later, wait. So you can open your QR code scanner. Sorry, wait. So how many people? We have 28. So should we take a picture first? Is it okay? Before we take the attendance, I think after attendance you will go out.
Boleh kat tu?
Boleh. Kenang-kenangan so anybody that can switch on the camera, you are most welcome to switch on the camera, and then we can take a picture for all of us. Okay, and then I will share in the group. So let's take a picture together. Okay. How many of you? Isma, Alif, Firdaus. Okay, quickly, so that we can take the attendance and then we can go out. Dia yang dalam kereta semua Alif nak pergi mana tu Alif? Okay, no problem. I'm still in FKE so saya masih dekat FKE. So I give you maybe 5 seconds to open your cameras and then we can take pictures and then we can take the attendance, okay? Okay, okay. For those of you who has just come to the group, to the Google Meet, maybe we can take a picture together. So I give you another 5 seconds so that we can switch on the camera. Okay, we can take the picture. Wait. I want to open the WhatsApp so that I can straight away paste in the WhatsApp. Okay, you also can you can also screenshot on your own as well. Wait, you see this. So where are we? Okay, 3, 2, 1. Okay, first picture. Wait, I will share in the straight away. I will share in the WhatsApp group. Okay, last picture. Okay, freestyle. Okay, 3, 2, 1. Okay, so I will paste in the WhatsApp group. Okay, so we can take the attendance now. Wait, I will share the screen again. Sorry. So I will share the screen again so you can open your QR code scanner. And take the attendance, okay? And take the attendance. Okay, so I open the QR code scanner. You can scan your attendance. So for those who has scanned the attendance, you can go out. Okay, so all the best to you for your final exam. Okay.
Thank you, Doctor.
Okay, welcome.
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 Thank you, Doctor.
Okay, welcome. Okay, welcome.
Thank you, Doctor.
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 Okay, welcome. All the best.
Thank you, Doctor.
Okay, welcome. Who else? 4 people, 4 students absent. Siapa lagi?
I can scan.
What's your name?
Amirul Amri.
Oh, Amir.
Amirul Amri.
Amirul Amri. Okay.
15.
Okay, done.
Okay. Thank you,
Doctor, can you
Doctor.
check? I scan.
Okay, what's your name?
Sundus.
Sundus? Sundus, you cannot scan the attendance? You already scanned the attendance.
Okay, Doctor.
Okay.
Thank you so much.
Okay.
Kumaran, Doctor.
What's your name?
Kumaran.
Kumaran.
Yeah.
Okay, Kumaran. Okay, sudah?
Okay, thank you, Doctor.
Okay, welcome.
Gabriel, Doctor.
Gabriel.
Yeah.
Gabriel. Okay, Gabriel sudah.
Okay, thank you,
Okay,
Doctor.
welcome. Siapa lagi ya? Any more? Okay, so that's all.